Hi there guys, welcome to this video where we're going to take a look at another interesting problem from mathematics, and we're going to take a closer look at the problem solving process and what that process looks like when it comes to trying to find the solution to non-routine problems. Okay, so the problem solving process is very messy, and it's that messiness and all of the difficulties that come along with the problem solving process that I really want to try to capture in these videos. Okay, so some problems obviously are more challenging than other problems. There's more difficulties that arise in some problems. Some problems are fairly straightforward with only a few difficulties. But whichever situation we find ourselves in, I want to present the problem solving process in all its messiness. Okay, so the problem that I've chosen for this particular video, and by the way, it's not the specific problem that I've chosen. I'm not aiming to just present a model solution to a specific problem. The problem and the specific solution to that problem are kind of beside the point. It's the process, how I personally arrived at a solution to that problem. Okay, so the problem that I've chosen for this particular video is the following, and it's from this book. It's a book in Polish, so it's Probabilistyka, Probabilistic, calculation of probabilities, mathematical statistics, and stochastic processes. The authors are Plucińska and Pluciński, and the problem is from page 52 in this book, and it's problem number 10. Okay, so problem number 10, the information that we're given is that, okay, so it says, let the events A, B, and C be pairwise independent. So we've got A, B, C are pairwise independent events. Independent, and we're also told that the intersection of A, B, and C is equal to the empty set. We're finally told that the probability of the complement of A is equal to the probability of B is equal to the probability of C, which equals lowercase p. Okay, so that is what we're told. This is not me misreading it. It is the complement of A here. And we're told to find the greatest possible value of P. Okay, what is the greatest possible value of P? So just before we get started, guys, this is a fairly new YouTube channel. At the time of making this video, I've only got a few subscribers, so I'd be really grateful if you would be able to hit the subscribe button and give this video a thumbs up, give it a like, and possibly leave a comment in the comments section. If there's anything that you're not sure about, if there's anything that you need clarification on, don't be afraid to ask in the comments section. I'll be happy to hear from you, and I'd love to help you. Okay, the aim of these videos is to help you with your problem solving when it comes to mathematics. So if you've got any questions, feel free to ask them. I'd be really grateful for your support, and I'd be really happy to help you. Okay, guys, let's have a look at this. So before you start solving a problem, first of all, make sure you've got a fairly clear idea about about the information that you've been given, what it means, that you've got a fairly precise understanding of it, and what it is that you're being asked to do. Okay, so it's often a problem. It's often an issue that comes up when I'm in my private tuition, doing one-to-one tuition with somebody, present them with a problem, and the problem might involve, let's say, I don't know, parallelogram. Okay, and so it might be, you know, a GCSE student, and they might have kind of a vague idea about what a parallelogram is, but they've got no precise idea about it. They've got no precise notion of what the various properties of a parallelogram are, such as it's a quadrilateral, or it's got two pairs of parallel sides, okay, and that the parallel sides are equal in length, and so on and so forth. Okay, there's all sorts of definitions that you could give of a parallelogram and various properties. If you don't have a precise understanding, if I ask somebody what's a parallelogram and they say, well, it's kind of like this, you can't use that when it comes to solving problems. To solve a problem involving, say, a parallelogram, you need to know in a precise sense, what a parallelogram is at the very least. And then hopefully you know some basic properties about parallelograms. You don't need to know everything, but as long as you know some basic properties, then you can at least start to make some attempt towards solving this particular problem. But if you don't know what a parallelogram is in a precise sense, that's something that you need to figure out first and foremost. And the same applies here, okay? We're told that A, B, and C are pairwise independent, okay? So before you start solving this problem, you need to make sure that you know what that means. What does it mean for events to be pairwise independent? Well, it means that if we take the events two at a time, they are statistically independent. Now, then you've got to ask yourself, do you know what it means for two events to be statistically independent or just independent? If your response to that is something along the lines of, well, two events are independent if they don't affect each other, which is often the response that I get, then again, how are you going to use that in solving your problem? You really need to have a precise articulation of what it means for two events to be statistically independent. So if we've got two events, X and Y are statistically independent, or we might just say independent, if the probability of X intersect Y is equal to probability of X times the probability of Y. Okay, there's other formulations that you can give, by the way, in terms of conditional probabilities and things like that, but this is a common formulation of the notion of statistical independence. Now, you might ask, how does this reflect the idea that two events don't affect each other? That's a separate problem, and it might actually be best answered by giving a different formulation in terms of conditional probabilities. But this is one way of defining statistical independence. One way, not the only way. The next problem that people have is that sometimes they don't see the full context. They see this formula, but they don't see the full context of what it means. So sometimes people will be kind of flicking through their textbook and they'll see something like this. And they'll think, so the probability of the intersection of two events is equal to the product of their individual probabilities. They won't necessarily see that this is only the case, that this equality holds if and only if the events are statistically independent. So generally speaking, this is not true unless X and Y are statistically independent. Okay, so you've got to have a very precise idea of what is going on here. Okay, so what does this mean then? It means that if we take A and B, the two events A and B, they are independent. The events A and C are independent. The events B and C are independent. What it does not imply is that A and B and C are all statistically independent, because there is the notion of statistical independence can be extended from two events to more than two events. But it's just because if we've got three events and they're pairwise independent doesn't mean that all three are independent. Okay, and this is a really important thing because it'd be very easy to fall into this trap, but it's just not true. Okay, so A, B, and C are pairwise independent. That means what? It means that probability of A intersect B is equal to the probability of A times the probability of B, which, going by the information that we've been given here, this is going to be equal to P times 1 minus P. So notice that the probability of the complement of A is equal to P, so that means that the probability of A is going to be 1 minus P. The probability of A intersect C is going to be probability of A times probability of C, which is likewise P times 1 minus P, and the probability of B intersect C is probability of B times the probability of C, which is P squared. Easy peasy. We've also got this, which means that the probability of A intersect B intersect C is going to be equal to 0. Okay, so if the intersection of A, B, and C is the empty set, the probability of this event is going to be equal to 0. So this for me is quite useful to do. Okay, before I really start delving into the problem, sometimes just collect your thoughts. Spend some time collecting your thoughts. What what does that, can you express this information in a much more usable form? Okay, so a usable form might be these equations, for example. The next thing that I chose to do here was to actually draw a diagram of this situation. Okay, so I'm going to try and draw it quite big. A Venn diagram. Okay, and with three events, A, B, and C. So we've got A, we've got B, and we've got C. Now, based on what I'm told, this event here, which is the intersection of all three, is basically doesn't exist. It's not there. Okay? So then I wanted to find expressions that would express that I could use to refer to these different regions. Okay? Now, because this is out of bounds, I can use, for example, in here, I can express this as basically the event A intersects C. Normally I would use the symbol A intersect C intersect not B to express this little bit here. But in this case, because A intersect C is equal to the event A intersect B intersect C union A intersect not B intersect C, and that this event is the empty set, then A intersect C is just A intersect not B intersect C. So that's what I write in here. And for similar reasons, in this bit I can write B intersect C, and in here, I'm going to have to swatch it in there, that's going to be A intersect B. In here, I can write A intersect not B intersect not C. In here, I can write A not A intersect B intersect not C. In here, not A intersect not B intersect C. And then finally, all around the outside, not A intersect not B intersect not C. So once I've got this sorted, and this is, for me personally, this is really useful. Okay, I like Venn diagrams, but if you're going to draw diagrams, always be careful. Okay, how you use the diagrams. Understand that a diagram is an aid to finding a solution to a problem, but you can't necessarily, in fact, you shouldn't really be making inferences directly from a diagram. You can use a diagram to motivate you to do certain things. So you can use a Venn diagram to give you some motivation, to give you a bit of a nudge in a certain direction. But let's say you look at the Venn diagram and you think you see something in your diagram. That what you see might just be a specific feature of how you've drawn that diagram. Okay, it might not be something that holds in general. Same for if you draw graphs of curves and things like this, or you draw a diagram, you've got two straight lines, and in your diagram it looks like two straight lines intersect at right angles, are perpendicular. If you infer from that those lines are perpendicular, then you're not working mathematically, you're not working logically there. By all means, if it looks like those lines are perpendicular, try to express that using algebraic techniques or some suitable techniques to show that is the case. But again, it might just be a feature of the diagram that you've drawn. Never take your diagram as expressing the truth. Okay, it's something that might give insight into the truth, but it doesn't necessarily express the actual truth. Okay, so what might I do from this point? Well, my idea was to try to find expressions for the probability of A, probability of B, and probability of C. Okay, why did I choose to do this? I don't know. It was just something that because I have expressions for each of these here, I guess that's where the idea came from. Because I know that A and C are independent, B and C are independent, A and B are independent. it just seems natural to me to use that information in some way. Okay, so if you're given some information, if you're not using that information, you might have difficulty solving the problem. Again, this is another issue that people have when it comes to solving problems. And if anybody's read George Polyer's book, How to Solve It, he does make a point of this. It really emphasizes this, that are you using all of the information that you've been given? Because it's very rare in a well-formulated problem for there to be superfluous information. It can happen sometimes, but in a well-formulated problem, there's not usually superfluous information. So if you've tried solving that problem, if you try solving that problem and you're not getting anywhere, and there's a bit of information that you haven't used, it might be because you don't fully understand that bit of information. You're not going to be able to solve the problem, because that bit of information is there for a reason. It's critical for you to solve this problem. So if you're told that such and such a triangle is a right-angled triangle, and you're not using the fact that the triangle is right-angled, and you're trying to solve this problem just effectively for general triangles, then surprise, surprise, you're probably not going to get the result that you want, okay, or that you're after. So make sure that you're using all of the information. So I've already used this bit of information here. Now I'm wanting to use these bits of information. I've already used these bits of information as well in deriving these. So let's start with probability of B. So the probability of B I can express as the sum of the probabilities of each of these three events. Okay, this bit here, the intersection of all three, A, B, and C, remember, is the empty set. So this is going to be the probability of A intersect B plus the probability of B intersect C plus the probability of not A intersect B intersect not C. So the probability of B I know is P. Probability of A intersect B is P times 1 minus P. Probability of B intersect C is P squared. And plus the probability of A bar intersect B intersect C bar. Okay, so what do I get here? I get P equals P minus P squared plus the probability of A bar intersect B intersect C bar. So cancel, 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 cancel. Oh dear. Probability of A bar intersect B intersect C bar equals 0. Okay, well, at first, when I first saw this, I thought, oh, surely I've made a mistake here. It's not impossible for this to be the case, but this is just not helpful. I'm wanting to find the maximum possible value of P. Okay, getting this result, really not helpful because P is just cancelled out. Okay, but I couldn't see anything wrong with what I'd done. So for the time being, I'm going to accept that result. Okay, so in other words, this bit here is kind of out. It's out of the picture. It's equal to 0. And now I can do a similar thing for A and C. Okay, so the probability of C is equal to the probability of A intersect C plus the probability of B intersect C plus the probability of A bar intersect B bar intersect C. And guess what? You get the probability of A bar. It's basically the same. In fact, it is basically an identical calculation to what we've just done. You get also that this is equal to 0. Okay, things are not looking good, right? Because I'm getting that all of these probabilities are equal to 0. These events are effectively the empty set. Okay, but we've still got one chance to go. Let's see. So as it stands, by the way, all we know is that P is going to be somewhere between 0 and 1. We can't necessarily narrow things down any further than that, really, although we can probably imagine that P is not equal to 0, because that would suggest that probability of B and C are going to be 0, which kind of makes it difficult when it comes to independence and things like that. So probably P is going to be greater than 0. But all we know is that P is somewhere between 0 and 1. Okay. So let's go for probability of A. So probability of A is going to be equal to the probability of A intersect B plus the probability of A intersect C plus the probability of A intersect not B intersect not C. So probability of A is 1 minus P, because we know that the probability of the complement of A is P, so probability of A is going to be 1 minus P. So probability of A intersect B is P times 1 minus P. Probability of A intersect C is also P times 1 minus P, plus the probability of A intersect not B intersect not C. So what do we get? 1 minus P equals P minus P squared plus P minus P squared plus the probability of A intersect B intersect not C. So the probability of A intersect not B intersect not C is going to be equal to, and I've got it as 1 minus P times 1 minus 2P. So it's a quadratic expression which factorizes to 1 minus P, 1 minus 2P. Okay. So we need this expression here. So this is non-zero. Fortunately, we've got something that's that could be non-zero. Although we require this probability can't be less than 0. So neither of these could be neither of these factors really can drop below 0. So we certainly need P to be less than or equal to 1. Otherwise, this would be less than 0. But we also require P to be less than a half, less than or equal to a half. Because when P is equal to a half, this will be 0. Okay? And therefore, this probability will be 0. So you could look at this as, you could draw the graph of this quadratic expression, find its roots and things like that. And what you'll find is that P is got to be less than or equal to a half. Okay, which would suggest potentially that the maximum value of P is going to be equal to a half. But there's one more calculation that we need to do. Okay. So let's get rid of this. Actually, I'm just going to make a note of. I'm going to leave that on because that's going to be useful to us. The final calculation that I want to calculate to do is A intersects, not A intersects not B intersects not C. Okay, I'm just going to look at refer to my notes, make sure that I'm not making any errors here. So this is going to be 1 minus the sum of these probabilities here. So the one that we've just calculated, so I'll write it in brackets. 1 minus P times 1 minus 2P minus A intersect C, which is P times 1 minus P, plus B intersect C plus A intersect B. Okay, which is going to be equal to, what do we get? You do all of the cancelling out and you just end up with P times 1 minus P. Okay, so we require this to be greater than or equal to 0 again. Well, to be between 0 and 1, so it's a probability. Well, this is going to be between 0 and 1 whenever P is between 0 and 1. So this actually doesn't give us any further refinements on our inequality for P. We needed to do it because it could have done. But all this tells us is that P is going to be between 0 and 1, which we already knew from the outset. That's going to be true for any probability anyway. So of all of the calculations that we've done, which are, I can't see any further calculations that we really need to do, it's this one that really gives us the restriction that we need on the possible values of P. Okay, And the restrictions that we get are that p is going to be less than, okay, 0 is less than or equal to p is less than or equal to a half, which suggests then that p equals a half is the maximum possible value for p. Okay, so that brings us to the end of the solution to this problem. If there's anything that you don't understand, anything that you want clarified, please leave a comment in the comments section. Feel free to ask. I'll be happy to help. That brings us to the end of this video. Cheers, guys.